So then, please give a warm welcome to Natasha. She is a product cybersecurity lead at Symbio, and she did a PhD in cybersecurity and deep learning to develop AI-driven solutions to address emerging cybersecurity challenge in mobility. Thanks for having you here.
Thank you. Thank you, everyone, for being here. Thank you. So, yes, I'm glad to be with you here today to be able to discuss one contribution, thanks to Scapy, that I have actually worked on throughout my PhD research thesis. The topic today will be focused on how we can actually build a data set that can help us train and test and validate artificial intelligence algorithms that are dedicated for intrusion detection systems in the automotive domain. The intrusion detection system that you see is called SED, and it's an AI-based intrusion detection system for some IP protocol. So I have another question for you. How many of you are familiar with the some IP protocol? Great. So for some of you who don't know me, I'm a product cybersecurity lead at Symbio. This is a company that does fuel cell systems, or this is a safety critical system for doing electricity out of hydrogen. And prior to that, I have been a consultant and an engineer in cybersecurity at Bosch ITAS. I have done my PhD in AI for automotive cybersecurity, and I have a technical expertise in AI security, intrusion detection system, and automotive cybersecurity. So let's get started. Today, I'm going to present to you the background and motivation behind using AI for intrusion detection system overall, and mainly on the topic related to automotive systems. Next, we will actually go into the threat model and the attacks that I have considered in order to build my dataset and to train my machine learning algorithms. And after that, I will be talking about how did Scapy had a critical role in building this dataset. What is the proposed framework for detecting the intrusions in an intelligent way? And we will show also the experiments results that I have obtained by leveraging the proposed framework that we'll see in section number 4. After that, we'll end into conclusions, research contributions, thanks to Scapy, and my wish list for Scapy after my experience on that. And so let's start with the background and with the motivation. So all of you might know and have experienced working with Automotive Ethernet. The main reason for switching from the controller area network that was built around the 1980s into the Automotive Ethernet is that we're having high bandwidth. So if you see on the figure on the right, we're moving into having new network technologies depending on the bandwidth that is urgently needed for integrating new automotive systems that require a huge amount of data being transmitted inside the EE architecture. And so, established by the Open Alliance, the Automotive Ethernet has been brought. And on top of the Automotive Ethernet technology, we are able to leverage different kind of services that could be highly inspired from the IT network domain. But as you can see, we have more and more codes that are being integrated into today's vehicles, and we need somehow a solution for this automotive software complexity. So in order to find solution for that, the SOM IP protocol has been developed, which is the scalable service-oriented middleware over IP that has key properties. So the first key property is that it supports the service-based communication approach in the EE architecture of the vehicle. It's compatible with AUTOSAR, it's scalable to be able to be used on different platforms and varying sizes, and it's adaptable to different kind of automotive operating systems. So a bit of reminder for those who already know some IP, and for those who don't know some IP, let's discover it a bit together. We have two devices that would like to exchange over the EE architecture of our vehicle, device A and device B. And these two devices need to, make any kind of service. Let's imagine to open a door. So the device A would be sending open the door to device B, and then the device B will respond back by saying, okay, I opened the door. For that, we need, so this is just a service that is related to opening a door out of the 4 doors in your vehicle. For the SumIP message that is going to be handling this service, we will be having two kind of features. As we already know in the IT domain, we have the header and the payload. So for the header, we'll be having different attributes. And as you know, in machine learning, when we have attributes, this can be helpful for classifying, categorizing, or even detecting anomalies. And so in the header of the SumIP protocol, we have the message ID that is composed of the service ID, so the identifiers for the services that is being going to be the device A will subscribe to. And we have also the method ID associated to that. The length will be the length of the payload and the section of the header we have. And then for sure we'll be having some request ID that is composed of the client ID and the session ID. So the client ID will be the unique identifier for the device requesting a certain service for the with the following service ID. And the session ID will be in like the identifier of the session where the client and the provider or the service provider will be actually exchanging through. Then we don't have to forget the protocol version, the interface version. These are considered as specs for the protocol we are using and the interface we're working on. The message type will be if we're sending a request, a response. So this is very specific to the message types that we're able to see in the SumIP protocol. So based on that, also you can see that we have in the payload like a series of input that can be also exchanged between the device A and the device B. So what are the communication patterns that we will be actually checking in the message type field? We'll be having method calls like the remote procedure calls. You can send a request, receive back a response. You can have some event callback. So the server is sending an event to the client, and you can have a notification also callback. So what we have to do in our threat model is to exploit each type of this communication pattern in order to build our data set with attacks. We can see that researchers have, since 2016, this was the only paper that talks about anomaly detection for SumIP. It wasn't done for the automotive domain, it was done for the aviation domain, where researchers from the Technical University of Munich, the TUM University, they have published how they can do anomaly detection without artificial intelligence. It was mainly using the complex event processing procedures. And then we have started to see research work coming back since 2020, where we have different kind of research regarding how to develop a novel security protocol for SumIP, or how to make a fuzzer, a gray box fuzzer for the SumIP protocol in the auto domain. So we can see that the interest started in 2016. There are papers that propose countermeasures regarding how to detect intrusions, others how to do fuzzing on the protocol, and others how to enhance the authentication for the SumIP protocol. In my contribution that I'm going to be talking about today, I want to shed the light a bit about how we can leverage the AI-based algorithms for that. And so the point is to be able to check what is the best representation of a data set that can help us flag an anomaly if there's, imagine, a denial of service attack happening between different components in the EE architecture. Or additionally, we are going to check how to detect anomaly when we have a long sequence of network packets. Like imagine 1,000 packets exchanged between devices, and there's only one packet that represents an anomaly. So will the traditional machine learning algorithms detect that, or we need more intelligence and more power into detecting these abnormal behaviors that represent an attack? And here I just want to shed a light on the fact that anomalies are not unintentional anomalies. We talk here about anomalies that represent cyber attacks on the network. And so you will see on the picture on the right the process that I'm going to dive deep into in order to build the data set. On the left, and on the right we will see how we're going to compare the intrusion detection system that is based on AI with other deep learning based algorithms. So what is the threat model that we're going to work on? I have chosen a threat model which is also based on the 2016 research paper. because they are the researchers, the main researchers who have built an open source SumIP generator tool that can actually be leveraged also for the automotive Ethernet that we can build a data set out of it. So here we can see that we have different servers. So these servers are the ECU that can give us a service in the vehicle. And we have different also clients that's going to subscribe to these services. We have chosen that, for those of you who are familiar with SumIP, you know that SumIP also lies on the SumIP SD protocol. So for the service discovery, we didn't consider that, even though that we know that there are attacks that are associated to the service discovery. And a lot of research papers talk about how we can actually abuse this service discovery in order to do man-in-the-middle attack. So here we have considered that a man-in-the-middle attacker is already exploiting the service discovery. It has also already a legitimate MAC address and a legitimate IP address. And what is going to happen is that, as we can see here, the man-in-the-middle attacker is going to be having a legitimate IP address and is going to exchange with all the servers and the client inside the network. So as you can see here, he's going to sniff the SumIP network traffic that is exchanged in the in-vehicle network, and he's going to transmit the packet to all the network participants so that he can show that he's impersonating some other SumIP services and the client's devices and services in the network. So based on the chosen threat model, we have actually decided to go for very basic scenarios just to be able to test the ability of AI to detect these deviations from the normal behavior, these intentional deviations. The first one is a request without response. So we simulate that an issue A is going to send a request to issue B, but it's going to be relayed by the attacker. So he's the man-in-the-middle attacker. So the issue A will not be receiving back the responses. The second one would be a response without request. So in this case, the issue A might be receiving different responses even though he didn't send a request. So this shows that a man-in-the-middle attacker is actually forging some packets to be sent in the network. And the third one is that an error is sent back on an error. So let's imagine that the issue A has sent the request to issue B. The issue B will send back an error. However, the attacker is going to also reply back with an error based on the sniffed error message. So based on, if you look at the AUTOSAR specifications for SumIP, you cannot send an error if you have already an error that is being sent. So, and the last one is going to be the error on event. So whenever the ECU A will be receiving an event, it cannot send a response back with an error. So you see, these are very basic deviations from the normal behavior, but this is the threat model that was brought up by the anomaly detection research paper in 2016 that shows how, based on their complex event processing procedure, they are able to create this kind of threat model on the system. So for the dataset generation, what we have actually decided is that first we have to do some parameter configuration. We have to decide which kind of SumIP services will be used in the network, which kind of devices are going to be chosen as clients, as servers, as attackers, which kind of attack type are we considering in the network. So here we mentioned that we're going to work on man-in-the-middle attack with some basic deviations from the normal behavior specified by AUTOSAR for SumIP. Then we have the number of attack executions, the minimum response time of the attacker, the maximum response time of the attacker. So these are all things that we are able to precise using the SumIP generator made by TUM University. After that, we generate, so you can see the SumIP generator will help us generate a pickup file that is showing the trace of packets that is exchanged inside the network. What we have to work on is to do the labeling, so to say if each packet represents a normal behavior or an abnormal behavior, to do feature extraction, and then so this is the machine, the dataset processing, so that we can able to have a balanced dataset that contains both attacks and also normal behavior, and then have it also labeled, because we're going to use a supervised machine learning algorithm and not an unsupervised machine learning algorithm. So you can see here that the main problem we had to face is how to transform the raw packets that we have received in the pickup file to some IP packets. So we urgently needed to know how to extract the some IP features. So to say this field represents a service identifier. This field represents a method ID. Because the point, as you can see here, we needed to make a tabular data set. And it's not easy. If you don't have a library that can help you do the job, you need to invest a lot of time in knowing how to actually separate the different attributes from the raw packet and make a tabular data. And our point also was to create different variants of the representation of the data to check how to apply the machine learning algorithm. So the first variant to have it all like binary data, but at least binary labeled data. And the second one was to have, like this data, some numerical and categorical data where we have actually machine learning algorithms that can work on that. And so what we did actually was to leverage the Automotive some IP contribution that was already done. And based on that, you can see that we have used some basic functionalities just to be able to retrieve the different attributes and construct a data set out of that. So we receive a pickup file, we just read it, and we try to actually do some processing on the data set so that we can have a big data set that is able to have different variants, one which is labeled numerical data that I have already explained, and the other one was to have labeled and categorical data. So you can see based on the, this was one of the main contributions for the Scapy to help us understand what is happening inside the data set. And for each set of the data set that we had to label each, let's say each packet, whether it's normal or abnormal. So this was a helpful contribution for us, and this led to the generation of the data set that is composed of 4 types of attacks. And you can see for each type of attack, we were able to make a training data set, a validation data set, and a testing data set, so that we can be able to validate the data before testing the model. So gladly, we were able to generate these 4 kinds of data set that you can see. They are mainly composed of the header. We didn't look for the first contribution on the payload. We just wanted to check how to assume intrusions just looking at the header of each packet that is exchanged between the different ECUs in the network. And so based on the data set that was generated, we were able to train a machine learning algorithm. Actually, it's a deep learning algorithm. It's based on attention-based mechanism. Maybe you have read the paper, Attention is All You Need, that was published in 2017 at Google, DeepMind. So the point of this paper was to be able to show how attention can be actually well exploited so that we are able to know how to leverage the interact with the sequential data. And in our case, we wanted to have a window of packets that are being exchanged. And if there's at least one anomaly in the packets, then we have to detect that there's an intrusion. And so you can see here that we take the input X, we do some processing on the input, we try to check if there's any contextual dependencies between the packets, like if there's a request, then I have to have a response here. So the model should be able to understand that. And after some processing that was done, we have the sigmoid function that's going to tell us if it's a binary answer, if there's an attack or not. The experimental results show us that when compared to other types of neural networks, like the recurrent neural network or the convolutional neural network, that SAD is actually performing the other deep learning algorithms based on the area under curve scores and based also on the false positive rate and the recall rate. We can see that it's actually decreasing the false positive rate for the majority of distributions introduction, which is actually a very critical, let's say, metric for the intrusion detection. And based on the computational results, we know that the long short-term memory and the recurrent neural network, they are very good for the sequential data, but the main issue behind that is that they are slow in detecting the attacks. So we needed to find a compromise. We need some efficient models, but at the same time, we need them to be running faster, especially if we're going to include them in the embedded systems. So after the development of the model, we were able to publish it through a research paper, and it was also available on GitHub, so you are able to access it and to check how it works. And I just want to conclude that we were able to actually build a robust intrusion detection system dataset that is only focused on the SUM-IP protocol. It's not focused on other automotive protocol layers. We proposed a novel deep learning intrusion detection system for SUM-IP that is based on attention mechanisms that are leveraged from the transformer architecture. And you will see that the proposed model, based on the evaluation metrics that we have obtained, it's computationally efficient, it achieves a great performance. The future work that we aim to have is actually to check how much a generative artificial intelligence algorithm are great in developing datasets. The main issue that we are facing in the automotive cybersecurity community when it comes to machine learning is to have great datasets. Usually, some OEMs, they can actually have great data set, but this is not published because this is intellectual property. It's like if you read the research papers from 2010 until now, we only have 2 great data sets, but that are just only focused on the controller area network. However, for the automotive Ethernet, we have just some let's say, toy example dataset that can help us do experiments, but for sure we need to go into scalable datasets that contains various automotive protocols for that. And so why not leveraging Gen AI for that and comparing it to non-GI based solutions. The second point I'd like to mention, we can see now that we have a lot of AI agent research papers that are being published, where we talk about how we can use LLM as a brain for the AI agent and to be able to do cybersecurity tasks. So why not have multi-agent systems for detecting intrusions on diverse protocols that can interact together and then can tell us if there's an attack that is being affecting diverse protocols in parallel. So these are one of the future work suggestions that I think for sure we can collaborate on to be able to have a great data set for not only for SUM-IP but for automotive Ethernet in general, and have multi-agent system that can help us detect intrusions for all the protocols on the automotive Ethernet. So I would like to thank Scapy because due to your hard effort on building this library, I was able to publish 2 research papers, one on the recurrent neural network use and one on the attention-based neural network for detecting attacks on the sequential data for the Scapy. And lastly, my wish list is why don't you have a VTP protocol in Scapy? This is one of the most important protocols, I would say, for the audio-video bridging and for the time-sensitive networking. There were 2 research papers that were actually published for the attacks on the AVTP. And when I started to work on the AVTP, unfortunately, I didn't have Scapy to support me on this, I would say. So I re-looked at the table that is mentioned on Scapy, where we have support for some IP, let's say OBT, XCP. But AVTP, I think, maybe you can correct me if I'm wrong or if I didn't search well, but there's no possibility to generate or to parse AVTP traffic. I wish, as I mentioned here, the full implementation of the IVTP dissector and packet crafting so that I can have my own syntactic dataset for the AVTP and to simulate the diverse kind of attack scenarios on that. And that brings me to the end of my presentation. Thank you for your attention, and I'd be happy to take your questions now.
Thank you very much for this great talk. So, do you have questions?
So I wonder how realistic the threat model actually is and whether it would be relevant to real-world scenarios, because the threats that I saw, if I would put a man in the middle, I would definitely not trigger those. So I don't have a solution to get to any real data other than maybe ask people that pen test vehicles, for example. How is there a plan to transition to real world data somehow, or make it more realistic?
Yes, for sure. So thank you for this question, because this shed lights on the threat model and how great it is to enhance it so that we can get to more realistic threats that are represented in the dataset. So as I mentioned in the presentation, the attacks are just representing some small deviations from what AutoSAR is telling us to do. When we specify how the SOM IP protocol should be well considered when exchanging packets between subscribers for any SOM IP service. But we should surely enhance the data. This is a call to action from my side on including more, first testing what are the vulnerabilities of SOM IP, and trying to check which kind of, let's take the stride threat model into consideration. Can we do spoofing? Can we do elevation of privilege? Can we do tampering on the SOM IP? How feasible? What is the attack feasibility rate of each of these threat scenarios on SOM IP? There aren't any published research paper and any published study about that. And try to have a bigger data set that is representative. But another thing, so this is just one side of answering the question. Yes, we should go for a better threat model. This is just a representation of how an attack can happen on SOM IP. And I would like also to say that the SOM IP protocol, actually we're starting to see some secure countermeasures that are currently being implemented in the SOM IP. So it's great also to check how feasible it is to do the attacks on the SOM IP protocol with some security that are currently being integrated. So yeah, I think we should go for having a bigger data set for sure.
Thank you. Another question?
First of all, amazing work here with and it's really cool that you used Scapy for the generating the dataset. I think it's a really nice out-of-the-box thinking.
Thank you.
In order to do it. But as also he asked as well, with how realistic it is not only to find or detect the attacks, but also how realistic it is to implement it at the end of the day in a vehicle, right? So we speak about resources and it's nice to see it on a research, but at the end of the day, it needs to be somehow implemented and be tested on a real vehicle. Is there any plan? Did you already try?
Exactly. So I was actually thinking with some of my colleagues at Telecom Paris to be able to have some basic demo that can help us just generate a better data set for that, which is some Raspberry Pis that are being connected so that we are able to transmit some IP messages. We can start at least from here. I mean, just for a demo example on how we can generate data out of that and how we can show some attacks that can be done on that. We still did not implement it yet, but I have seen one research article that is doing the same. He took just 2 ECUs that are exchanging. These ECUs are represented as Raspberry Pis and just one router because we are working here on Automotive Ethernet. And with maybe he considered also 2 other ECUs. I don't remember because it was 3 years ago. And he made a research paper out of that, but he didn't publish the dataset. I don't know why, when it comes to Automotive Ethernet, we don't have reliable or huge datasets with the enriched threat models that we can work on. Maybe we should push for having this in the community so that we are able to, because we have the tools to process the data, so we only need the data so that we can process well.
Okay, thank you. Another question? Yeah.
Regarding the dataset, regarding obtaining realistic datasets, my question would be, is it necessary that your dataset also contains the intrusions? Can this approach only detect the intrusions that it is trained on? Because if not, then it will be easy to just take a bunch of cars, connect devices to sniff all of the automotive internet traffic and just give you gigabytes or terabytes of data. But if I need to include the specific intrusions that need to be detected, then yeah, I don't. Does it mean that this system can only detect intrusions that are known? Let's say.
Yeah, I really like this question, and this is one of the questions that I asked for the previous talk. The first thing we have to imagine or to think about in machine learning is, first, what is the learning algorithm that I'm going to work on for the problem that I need to solve? In machine learning, let's say, or in artificial intelligence in general, we have three main type of learning approaches: the supervised learning, the unsupervised learning, the semi-supervised learning, and we have also the reinforcement learning. So in the supervised learning, if you're going to apply it for intrusion detection, we need a labeled data set first, and which is balanced. So we need the same amount of attacks and the same amount of normal behavior. But if we're working on unsupervised machine learning, we can just focus on having a good representation of the normal behavior. And any kind of, during the testing, so for the training, we just need the normal data set that is available for training the model, so that the model can learn well the normal distribution of the, let's say, some IP network traffic. In the testing, we can surely have the attacks, and it can flag us whenever it can check that there's a huge deviation from the normal behavior. In the semi-supervised learning, this is also can be considered, where we have only let's say, the normal data set that is considered, and this is something we can use and leverage in the autoencoder, where we use an autoencoder-based neural network to be able just to make a distribution of the representation of the distribution of the normal behavior. And this is one of the research works that I have worked on for the controller area network and also for the AVTP network. Yeah, so the question, my answer would be briefly, it all depends on which kind of learning algorithm you should go for. And for sure, what I would recommend is to use the unsupervised and the semi-supervised, because as you mentioned, we always have 0 days attacks and 0 days vulnerabilities to consider.
Thank you very much. Other questions? Okay, I don't see anyone. Thank you very much for this great talk.
Thanks to you.
Being here.
Thank you.